In section 13.3, we address Hamilton paths and circuits. In the previous two sections, we defined general paths and circuits and Euler paths and circuits. Now we're going to focus on the definition of Hamilton paths and circuits. The first two questions, true and false, ask us to go through and review what we already know about the general and Euler paths and circuits. In general, a path must pass through a vertex only once. Well, in general, we don't have any requirements for where our path goes or what it includes, so that's false. An Euler path must pass through a vertex only once. If you remember from our definition for Euler paths and circuits, we talk about every edge exactly one time. Every edge exactly once. So all of those E's, every edge exactly once. Doesn't address vertices at all. So that's false. A general path must pass through an edge only once. Again, no requirements for general paths. An Euler path must pass through an edge only once. That's true. That's our definition for Euler path and circuit. All right, number 2. A path must pass through each vertex. No, we don't have any requirements, again, for general paths, so it's false that it must pass through each edge. An Euler path, however, must pass through each edge. That is true. That goes back to our definition for Euler paths and circuits. Now let's talk about Hamilton paths and circuits. Hamilton paths and circuits, instead of focusing on edges, focus on vertices. A Hamilton path is a path that contains each vertex exactly once. So instead of each edge exactly once, like Euler, now it's each vertex exactly once. The difference with a circuit is that since a circuit has to start and stop at the same vertex, that one vertex, the beginning, gets to be repeated at the end, and it goes through all the other vertices exactly once. So true or false based on that definition. A Hamilton path must pass through a vertex only once. That's true. Must pass through each vertex. That's true. Must pass through each edge. That's false. However, it's good to note that while the Hamilton path doesn't have to go through every edge, doesn't have to travel every edge, but it will never repeat an edge. Which makes sense if you think about it. Because since it can't repeat a vertex, that means it can't go back over an edge, because then it would have to go back to that vertex. Let's look at the second page. At the top, you find that we have a chart that focuses on Hamilton, all three of our different definitions for paths and circuits. First, we have our general paths and circuits listed. Then we have Euler, and then we have the Hamilton paths and circuits. So we're going to take those in blocks. Remember, each path is a circuit. And let's look at the general paths and circuits first. Well, our columns all focus on either every edge exactly once, each vertex only once. None of that is required for our general paths and general circuits. So we're just going to say no, that's not necessary. Then we move on to Euler paths and Euler circuits. And remember, Euler starts with E, so it focuses on each edge exactly once. So that's true for these first two columns for Euler paths and circuits. We don't have any requirements about vertices when we're talking about Euler. When we get to Hamilton paths and circuits, though, that we introduced today, now we're focused on the vertices. Hamilton paths and circuits pass through all the vertices only once, with that little disclaimer, because the circuit has to start at the beginning and ending at the same one. That one gets to be repeated. We don't care whether or not they go through all the edges, but because we can't repeat a vertex, we aren't going to repeat any edges. So that gets included in our Hamilton paths and circuits because of the definition. Number 6, true or false. There are Hamilton circuits which are not Hamilton paths. Well, that has to be false because remember that every circuit is a path, right? In general, every circuit is first a path. It's just a path that begins and ends at the same place. So that means that every Hamilton circuit is also a Hamilton path, and we want to do our quick Venn diagram. All right, now we have two to check. We have been proposed that this is a Hamilton path and proposed that this is a Hamilton circuit, and we want to check if they actually are or not. So when we start with A to decide if this is a Hamilton path, we know that a Hamilton path goes through every vertex exactly one time. How many vertices do we have? We have 12 vertices. So I'm going to count and make sure that all 12 are listed. I'm going to make sure that none are repeated. So I'll go through my alphabet and make sure they're all there. They are. So now the last step is to check to see if it actually works. So ABF leads me to go this way. IKE, IKE, GLJ, GLJ, HDC. I've hit every vertex exactly one time. I haven't repeated any. I've missed some edges, but that's fine. It's true, this is a Hamilton path. So let's look at the next one. Is it a Hamilton circuit? Well, it begins and ends at the same vertex, so that's a good start. Now I need to make sure that every other vertex is included and none are repeated. What do you think? Well, hopefully you notice that J repeats, and that's against the rules for a Hamilton circuit. So this is not a Hamilton circuit. I don't even have to bother with checking. Okay, let's look at the next page. It says to find a Hamilton path that begins with A and ends with B. I want you to pause your video and see if you can do that. You're going to start with A, you're going to end with B. I've got a total of 1, 2, 3, 4, 5, 6, 7 vertices. So I already have 2 listed. The other 5 need to be in here in a certain order. And I think that there's more than one way to go because I can leave from A to D or A to F. You know what though? I think that there is just one way to go because if I go to F and make my way around, I'm over here at D. I don't have any way to get back to B. So I'm going to have to start A to D. So pause your video, work out that path, then work out the circuit on number 9, and then restart your video. Okay, so hopefully you discovered that if you travel around the outside and then up to B, there is your Hamilton path. Every vertex has gone through at least once. No edges are repeated. We did leave out edges, but that's fine. The next one asks you to find a Hamilton circuit that starts with AB. Well, a circuit is going to start and end at A. If I travel around the outside edge of my graph, I go from A to back to A. A, B, E, D, A, B, E, D, F, C, A is that Hamilton circuit. Okay. Complete graph, a new definition. We talked about disconnected and connected graphs. Now we're going to talk about complete versus not complete graphs. A complete graph is a graph that has exactly one edge between each pair of vertices. So, for example, this first graph given is complete because I can start at any vertex and go to the other 3 directly. So if I'm at C, I can go directly to A, to B, or to D. If I'm at A, I can go directly to C, to D, or to B. So I have exactly one edge between each pair of vertices. This graph is complete. This next graph is not complete because I'm missing a couple of those edges. I don't have every connection available to me. All right, let's look at page 4. Can you find a Hamilton circuit? So we're going to start setting up some possibilities here as we work through the next couple of pages. Can you find a Hamilton circuit that goes through each vertex only once? And then it asks if the graph is complete and how many vertices there are. We'll do this first one together, and then I'm going to pause the video and give you an opportunity to work through 13 through 16, and we'll talk about the rest then. So can you find a Hamilton circuit that goes through vertex E only once? Because if I start, say if I start at A, I can only get here, and then I would have to go through E to get back to A. I could start at B, the same thing. Even if I started at E, I can't help but go through, repeat E more times than I should. So no, that's not possible. The graph is not complete because I'm missing those connections. There are 5 vertices. 1, 2, 3, 4, 5. Okay, you guys do 13 through 16 with your video paused. Okay, so here are questions 13 and 14. You can find a Hamilton circuit here that goes through E only once. If I start at E, I can travel either to B first and work my way around back to E, or I can start at E and go to D first, work my way around back to E. Both of these are Hamilton circuits. It's not a complete graph. I'm missing this edge. There are 5 vertices. So both of these first two graphs have 5 vertices. Neither one is complete. One of them I can find the Hamilton circuit, one of them I can't. Number 14 has 4 vertices. It's a complete graph, and yes, I have Hamilton circuits. I can start at any of the 4 vertices, travel around the outside, and make my way back. On the next page, number 15, it's not complete again. I'm missing this edge, and I can't do a circuit because I can't get back to A without retracing and going back through. There are only 3 vertices. And then on 16, you can't find a Hamilton circuit because I can't repeat an edge. So the only way to get through this as a Hamilton circuit would be to repeat that edge, and I'm not supposed to do that. Even though the graph is complete, there's no Hamilton circuit. There are 2 vertices there. So number 17, this isn't really enough examples for us to discover this, but number 17, what 2 characteristics guarantee that I will have a Hamilton circuit? Well, I didn't have one here. I didn't have one in number 15. I did have one in 13 and 14. 14 is complete, 13 isn't. And I had 5 vertices in both of these. They were both not complete. I was able to find a Hamilton circuit here and not there. So with these few examples, it's kind of confusing. But here are the 2 things that will guarantee I have a Hamilton circuit. First, if I have a complete graph, I know I will have a Hamilton circuit, as long as the graph has at least 3 vertices, more than or equal to 3 vertices. If both of these things happen, I know I have a Hamilton circuit. If just one of them happens, I might have a Hamilton circuit, but I might not have a Hamilton circuit. Okay, true or false? Complete graphs always have a Hamilton circuit. Well, that's false, because right above on number 16, it's complete, but it doesn't have a Hamilton circuit. Incomplete graphs always have a Hamilton circuit. Well, that's false, because number 15 and which other one? Let me look back. Incomplete graphs. Number 12 were incomplete, did not have a Hamilton circuit. Incomplete graphs never have a Hamilton circuit. That's false as well. If you look at number 13, 13 was an example of an incomplete graph that did have a Hamilton circuit. So the only way to guarantee that I for sure will have one is to make sure that I have at least 3 vertices and a complete graph. Okay. Number 19 on the next page, consider that graph. I'm given 2 circuits. Are they Hamilton circuits? Well, do they go through every vertex one time exactly, except for that first vertex? Yes, they do. Are they distinct? Do they go through different edges? No, they're not. They go through the same 4 edges. If I trace C, A, B, D, C, and then I trace A, B, D, C, A, I've traced the exact same 4 edges. We have a formula introduced. This formula tells us the number of unique or distinct Hamilton circuits when I have a complete graph. Where I know how many vertices I have, so n is equal to the number of vertices, I can take n minus 1 factorial to figure out how many unique or distinct Hamilton circuits I have. For example, If I know that I have 8 vertices, if I have a graph with 8 vertices, that means n equals 8. So I would have 8 minus 1, or 7 factorial distinct Hamilton circuits. How do I do a factorial? Well, I start with the number given and I multiply my way down to 1. 7 times 6 times 5 times 4 times 3 times 2 times 1. Or I can use that probability button on my calculator. Remember your probability button right here? If I want to find 7 factorial, I input 7, push that probability button, and go across to the exclamation point. That's my 7 factorial of 5040. That's how many unique Hamilton circuits I will have. So up here for this graph, n is 4, which means I would have 4 minus 1, or 3 factorial unique Hamilton circuits. 3 factorial is just 6. So I would have a total of 6 unique Hamilton circuits. What if I have 6 vertices? Well, n equals 6 gives me 5 factorial, which is 5 times 4 times 3 times 2 times 1, or 120 Hamilton circuits. All right, determine if the graph is guaranteed to have Hamilton circuits, and if so, figure out how many. What guarantees that it will have Hamilton circuits? What makes this happen? Remember, there were 2 things. First, it had to be a complete graph, and second, it had to have at least 3 vertices, so 3 or more vertices. Is this a complete graph? It has more than 3 vertices, but it's not a complete graph. Look, I'm missing an edge here, and I'm missing an edge here, and I'm missing an edge here, and that has 2 edges, so that doesn't work either. So this is not complete. Not complete. I'm not guaranteed to have Hamilton circuits. All right. Answer that same question, work out that same value for numbers 24, 25, and 26 on the next page, and then restart your video. Okay, so here are the results that I got. Hopefully you got the same thing. Notice that this complex graph down here on number 26 has lots of vertices, but I'm missing some edges. Let's see, we've got A to F, we do not have an edge directly from A to H, and because that's not there, we don't even have to check for anything else. As soon as I find one pair of vertices without exactly one edge connecting them, I'm done. So that means that my graph is not complete, and I don't have to finish working out the possible numbers of Hamilton circuits. Okay, number 27 is a weighted graph. A weighted graph is a graph whose edges have numbers attached to them. Now, we're going to use this weighted graph to answer the next 2 questions. The weights can refer to miles, they can refer to dollars, they can refer to time, but I am weighting the edges so that if I take a certain journey, I know how much it costs me. And that cost can be terms, again, of distance, of time, of dollars, of anything that could calculate as something that has value. So let's find the weight of edge CE. Edge CE is right here. The weight of edge CE is 21. Let's find the total weight of this Hamilton circuit, A to B, F, G, D, E, C, A. So every time I have a connection between 2 vertices, I have an edge, and each of those edges has a weight. So I need to travel 1, 2, 3, 4, 5, 6, 7 edges, and I need to find the sum of those weights. What is the weight of edge AB? Well, that's 6. And then B to F is 18. And then F to G is 15. G to D is 18. D to E is 11. E to C is 21, and then C back to A is also 21. So once I've written all these down, I add them up and I find the weight of that circuit is 110. Now, when we're talking about weighting circuits, we're talking about what is traditionally called the traveling salesman problem. Now, a traveling salesman problem isn't always about sales, and it isn't always about a traveling salesman even, but it's just a way to refer to trying to minimize whatever the weight is. The problem of finding a Hamilton circuit in which a complete weighted graph for which the sum of the weights is a minimum. So when we're doing traveling salesman, we're looking for the optimal solution that gives us that minimum weight. So think about this. This goes back to that UPS article that we read before we started graph theory, where we talked about how much money it costs UPS or FedEx or Amazon or any of these big delivery places if they go even just an extra couple of miles a day per truck, or if they don't package or pack their vehicles correctly, if they don't take the best route, how much more it costs them. So finding that optimal solution is a big money difference. It could be actually traveling somewhere, like if you have pharmaceutical representatives who go to different doctors' offices in different cities. Maybe they need to do it as quickly as possible, so they're looking for flights that are timed correctly. Or maybe it's about the money they have to spend in their travel, so they're looking for the cheapest set of flights to get them through their route and then back home. But they're always going somewhere and then they're coming back home because it's a circuit. Which of these is not an element that every traveling salesman problem has? Well, you don't have to have a set of goods. That doesn't have to exist. You have to have sites or places. You have to have costs or weights. That cost could be in terms of money, but it could also be in terms of time or miles or anything else like that. And you have to have a traveler, somebody who is making the circuit. Okay, let's look at the next page and work out some of these traveling salesman problems. So in number 32, the diagram shows the distances in miles between 4 cities, just A, B, C, D. A businessman has to travel between all 4 cities, starting and ending at his home city A. So this is necessity, our starting and stopping point. If he lived somewhere else, he would start and stop somewhere else, excuse me. But he lives in city A. He wants to know the optimal tour in terms of distance that will get him to all the 3 other cities and then back home. So the variable we want to minimize, our cost variable in this case, is that distance traveled. So maybe he's trying to put the least number of miles on his car. Okay, so the brute force method means that we are going to check all the possibilities and to see what each of those solutions are. And then we'll determine from that for sure what is the optimal solution. The brute force method is the way to be sure we have the optimal solution. So to do that, we're going to say, okay, we've got our weighted graph. How many Hamilton circuits do we have that we need to check? Well, we only have 4 vertices, n equals 4. So that means we have 3 factorial or 6 Hamilton circuits that we need to check. The first thing is to list out all of those 6 possible Hamilton circuits. Now remember that all of our circuits we're going to list are going to start at A. So we are going to have 6 different circuits, and we're going to start them all from vertex A. Well, when I leave A, I can either go to B, I can go to C, or I can go to D. So I'm going to go to A to B, and then go ahead and skip one. I'll tell you why in a minute. A to C, skip one, A to D in your list. Okay? When I go from A to B, after I leave B, I can head to either C or D. So I can go A, B, C, or I can go A, B, D. And then I need to do the other one. So if I did A, B, C, I still have to hit D before I go back to A. If I did A, B, D, I still have to hit C before I go back to A. You see our organization? So I can go from A to B to C or to D. And then once I'm there, I have two options. So it's going to be A, B, A, B, A, C, A, C, A, D, A, D. Okay, what if I go A to C? Well, if I go A to C, then I can choose whether to go to B or D first. Once I'm at that vertex, I still need to go to the other one and then back to A. If I choose to go to D first, I can go to either B or C next. And then if I'm at B, I still have to hit C before I go home. If I'm at C, I still have to hit B before I go home. So that gives me my 6 Hamilton circuits that are possible. Now I need to find the weight of each of those edges and add them up. So look for the weights for each of these edges and find the sum. For this first one, we'll do the first one together. I'm going to have 1, 2, 3, 4 edges traveled for each. So I'm going to be summing 4 different weights for each. For number 1, I have edge AB, which has a weight of 100. Then BC has a weight of 125. CD has a weight of 110. And D back to A has a weight of 120. When I plug that into my calculator, I get a sum of 455. When I go to the second one, I have AB again because I start the same way, but then I take the edge from B to D, which is just 95. Then from D to C is 110 and C to A is 145, so I get a sum of 450. You see that the paths don't have the circuits, don't have the same weights. I'm going to pause my video, you pause yours, fill in the weights for those remaining 4 pathways. When you find the weight of all 6 circuits, you discover that they repeat. You don't have 6 different weights. The more vertices you would need to check, the more differences you would probably find in those weights of the circuits. When we have fewer vertices, we've got fewer edges to be combined in different ways, so we have fewer solutions. I see that I have a repeated optimal solution. The shortest amount of travel is going to be 450 miles. And that is by taking either this circuit or this circuit, going from ABDCA or ACDBA, because that adds the same set of edges. This is our brute force method. It guarantees that we get an optimal solution. Let's do another example of our brute force method. We have another weighted graph. It has 4 vertices again. So we have a total of 6 circuits to check. We are going to choose to start at B. We would get a different set of solutions depending at which set of circuits where we start. We're going to start at B. So remember, you're going to have those 6. We're practicing the brute force method one more time. If we start at B, we can either go BA, BC, or BD. And once we get to that second point, we have 2 choices. So if we go BA, then we either do C or D next, back to B. If we go BC, we either go D or A next, and then back to B. If we go from B to D, we either go C or A next, and then back to B. So I want you to find the weights for those 6 circuits. Pause the video, do that, and then come back. Okay, so I showed you step by step the first 2. So you can kind of check yours against mine and make sure you're doing the correct thing. Notice that we only got 2 different answers on this, 2 different solutions. The optimal solution is that 111, and 111 can happen from 4 different circuits. So the optimal solution is that value 111, and I can get it from either of those 4 options. Any of those 4 options. Okay, this next one is a practice problem. It puts a little bit more context in it. We are going to build our graph this time. We've got a bank security guard who has to leave his office every hour during his shift and check the status of the bank's front door, side door, and back door. So that's 4 different places. He starts at the office, he checks 3 doors, and then he goes back to the office. So that's a circuit he makes every hour. The distances between these locations are summarized in this chart. We are going to represent this with a complete graph, then use the brute force method to discover what is the optimal minimum distance. So we could, optimal solution is typically minimum. What if the guard was trying to get as many steps in as possible? Well, then his optimal solution would be the maximum distance, but he is wanting to take as few steps as possible. So he wants the minimum distance for his rounds. Our first step is to create our graph. He's going to start at the office. He's got to check the back door. He has to check the side door, and he has to check the front door. A complete graph connects each of these to each other vertex with as few edges as possible. So only one edge between each pair of vertices. So that's what my graph is going to generally look like. And then I need to put in the weights. Make sure you can read the chart. The distance, there isn't a distance between the office and the office because it's the same place. The distance from the office to the back door is 31 feet. Now notice that you can read down the column or across the row, and it doesn't matter. Office to back door is 31 feet. Office to back door is 31 feet. It gets listed twice. So the distance from the office to the back door is 31 feet. How about the office to the front door? Well, that is 83 feet. And the office to the side door is 52 feet. We're still missing some weights. How about the front door to the back door? Well, the front door to the back door is 119 feet. The front door to the side door is 35 feet. And the side door to the back door is 72 feet. So we have 1, 2, 3, 4, 5, 6 edges, each with their own distinct weight. Now, do the brute force algorithm. Find the 6 different circuits, sum them like we did in the last 2 problems, and figure out what is the optimal solution. Go ahead and pause the video, work it out. I'm not going to do it. I'm just going to give you the answer. So you work out the brute force method. Hopefully you discovered that the minimum distance for his rounds is 221 feet. That's my optimal solution. One way to get that would be office, back door, side door, front door, office. Okay, let's look at the next page. If you don't have the time, or maybe you don't need to be certain you have the optimal solution, good enough is really good enough. Instead of using the brute force method, you have the choice of using what we call the nearest neighbor method. It will get you an approximate optimal solution. You're not guaranteed it's the lowest weight, but it's going to be one of the lower values. You model the problem with a graph just like you did before. You figure out where you need to start. And then from that starting point, you always choose the edge with the smallest weight. You always choose the edge with the smallest weight. So you work your way around the circuit, always picking the lowest value that's available to you until you're done. Now, the nearest neighbor method does not guarantee an optimal solution. Does not guarantee an optimal solution. It will give an approximate solution. So here's our first example of using the nearest neighbor method to find the optimal solution. If we start, and we're going to do it a couple of different ways. We're going to do it first starting at C. If I start at C, what is my least weight where I can travel? Well, going from C to B has a weight of 21, and that's the lowest of those 3 options. So going from C to B is 21. Now I'm at B. I've already been to C, so I have to either go to A or D. Which one of those has the least weight? Well, my edge that takes me to D is just 37. So I'm going to go from B to D. Now I'm at D. I still need to go to A before I go back to C. That's the only other way I need to go. So I've got to go to A. That's 18. And then I have to travel back to C, and that's 35. So the weight of that circuit is 111. Now, I tricked you a little bit because this is one of the circuits that we already did. If you go back to the last time that we did the brute force together, that's the same graph, that's the same chart. We started with C instead of with B, but that's okay. We got the same value, that 111. Okay, that ends up being the optimal solution. That ends up being the least value combination of those pathways that's available. Okay, optimal solution, the nearest neighbor method does not always give me the optimal solution, but it gives me a good solution. John is a traveling salesman for a pharmaceutical company. His territory includes 5 cities, and he needs to find the least expensive route. So our weights here are dollars. The least expensive route to the cities and home. He's going to start and end at A because that's where he lives. And we're going to use the nearest neighbor method. Now, why might it be good to use the nearest neighbor method? Here I have 5 vertices, which means to find all possible solutions, I would need to do 4 factorial, which is 4 times 3 times 2 times 1, which is 24 possible Hamilton circuits. I would have to do 24, not 6. Well, that's way too time consuming for us to do by hand. So instead of using brute force, we're going to do nearest neighbor method. Now he lives at A. What's the nearest neighbor to A in terms of dollars? That's what's represented here. Well, if I look at those 4 pathways, the cheapest route is going to go from A to E at 95. So where am I going to go from there? Now I'm at E. I can go to D, C, or B. What is the cheapest one then? Well, the cheapest one here is to go from E to D because that's 151. Okay, now I've done A, E, D. I can go from D to either C or B. Which is the nearest neighbor? Well, D to B is going to be the nearest neighbor. That's 87. And I still have to go to C before I can go home. So my only choice there is that 152. And then back home, C, and then back to A gives me 250. 1, 2, 3, 4, 5 edges traveled. That nearest neighbor method gets us a total in money of $735 if you add that up. Play around with it a little bit, see if you think that is the optimal solution. That's my nearest neighbor method. Is it optimal? Try some other choices and see if you can beat 735. Well, if you play with it for a while, you find out that no, that's not the optimal solution. I can get 668 if I go a different way. In fact, if I go A, E, D, and then switch these two and do C, B, and then back to A, it saves me some money. Okay, so the nearest neighbor method does not always give us the optimal solution, but it does give us a good solution. And it's good enough when it's going to be so much longer to do the brute force method. Now, if you have a computer and an algorithm to calculate all the possibilities for you, that brute force method is a lot easier. One more example, one more practice problem before we're done. Costs of one-way flights between several U.S. cities are listed. We've got St. Louis, Kansas City, Oklahoma City, Des Moines, and Little Rock. So we have 5 different cities. You first need to set up your graph, do the weighted edges, and then calculate using nearest neighbor if you leave and come back to Des Moines. Okay. So here we go. Here's what the graph should look like with the weighted edges in all of your 5 cities. Here's my nearest neighbor method, starting at Des Moines and coming back to Des Moines. I come in at $811. Now, just to practice, I did some starting in St. Louis instead of Des Moines. This is just a separate practice problem. I found 3 different versions. I used the nearest neighbor method, and then I did a couple of different ways. I got it down to 864. But he doesn't live in St. Louis. He lives in Des Moines. What I would ask you to do is find Des Moines, and that's what that should come out to be.